Next topic we're going to look at is calorimetry, which is also in chapter 5. Calorimetry is going to be another way where we can experimentally determine the delta H value for a reaction. So calorimetry is the heat of the reaction. So we're using this to kind of experimentally determine through heat flow accumulation the heat of this reaction. So calorimetry itself is the measurement of heat flow, and then the calorimeter is the device we use to measure heat flow. So as you can see here, we have an example of a calorimeter. This is a bomb calorimeter. The ones we'll be using in class are literally just going to be two styrofoam cups nested within each other. They make pretty good insulators. So heat. There's different things we can look at when we're looking at heat capacity. So the heat capacity of something is the amount of heat required to raise the temperature of an object 1 Kelvin or 1 degree Celsius. It's the same increment. So there's two types of heat capacities we're going to look at. There's molar heat capacity, which is capital C with a subscript M. That is the heat capacity of 1 mole of a substance. Then specific heat, which is C with a little s, is the heat capacity of 1 gram of a substance. For the most part, during AP chemistry, you're really only going to be dealing with specific heat. However, you should still know about molar heat capacity. So a generalized question would be, do substances with a high specific heat heat up slowly or quickly, and why? So these types of substances will heat up slowly. If something has a high heat capacity, so something like water has a very high heat capacity. So remember, the specific heat is the amount of heat it takes to raise 1 gram of a substance 1 degree Celsius. So if you have a high specific heat, it's going to take you a longer time to heat something up. However, it will hold the heat in better. It'll also take a long time to cool down. Something with a low specific heat, something like copper or aluminum, those are going to heat up really quickly. So that's why your pots and pans are kind of made up of these metals that have a very low specific heat capacity. Makes sense because you want the pan to heat up quickly. You want to be sitting there for 10 years waiting for your pan to heat up. So this is the heat equation we're going to be using. Q equals mc delta T. I like to refer to it as Q equals mcat. Easy way to remember it. You should be familiar with this equation. You should have seen something like it last year. So Q is our heat lost or gained. That is measured in joules for this. So this is going to be in a joule. Mass for this specific equation is always going to be measured in grams. Specific heat capacity is usually given in joules per gram degree Celsius. They could give you in grams, Kelvin, but it's going to be in the same thing anyway, so it doesn't really matter. And then your delta T is your change in temperature. You can use Celsius in this equation. Remember, I know we just came off of gases. Gases, you must use Kelvin, but in this heat equation, you really can just use Celsius. That will be fine. So the type of calorimetry we're going to be doing the most is a constant pressure calorimetry. And this is what I was talking about before with this kind of coffee cup setup here. And this is what we'll be doing in class. We'll have this, it'll be usually be 2 coffee cups nested inside of each other. And then you'll have a thermometer in there. Usually I just keep a lid on it so that there's no heat escaping to the atmosphere. And since it's just a coffee cup, we can assume there is going to be constant pressure. It will just be the pressure of the room. So even when, if you want to say that the lid is a seal, it's not really a seal because there's air flowing in and out, but you just want to make sure there's not a lot of heat is being lost from the water. So we try to just put a little lid on it. So we always assume that our calorimeter is perfectly insulated. So any heat released or absorbed by the reaction will raise or lower the temperature of the water. And this is important because the reaction that's occurring, remember, that is the system. And then your water is part of these surroundings. So how your system affects the temperature of the water is going to tell you if there's an exo or endothermic reaction happening. So as we know, an exothermic reaction releases energy. So that's going to be a negative delta H. However, the water is going to either absorb or release this energy. In the case of an exothermic reaction, the water will absorb the energy. Therefore, if the water absorbs the energy, the temperature of the water should increase. On the other hand, in an endothermic reaction, you're going to have a positive delta H. Remember, endothermic means it's absorbing energy from its surroundings, and in this case, in a calorimeter, the water are the surroundings. So the water is releasing energy to this exothermic reaction. The endothermic reaction is absorbing energy from the water. This will lead to a decrease in the temperature of the water. So this is very important because what's happening to the water is the opposite of what's happening to the reaction. So that's why we say the heat of the solution is the negative heat of the reaction. Because as we just saw before, what's happening to the surroundings is the opposite of what's really occurring in the reaction. And just to keep in mind, for dilute solutions, we're going to assume that the specific heat is that of water, and water is 4.18 joules per gram Kelvin, or you could say 4.18 joules per gram degree Celsius. It's the same number. So practice problem here. A student is mixing 50 mLs of 1 molar HCl and 50 mLs of 1 molar NaOH in a coffee cup calorimeter. The temperature of the resultant solution increases from 21 to 27.5 degrees Celsius. Calculate the enthalpy change for the reaction in kilojoules per mole HCl, assuming that the calorimeter loses only a negligible quantity of heat and that the total volume of the solution is 100 mLs, its density is 1 gram per milliliter, and its specific heat is 4.18. So I circled this kilojoules per mole HCl because we need to know what we're solving the heat in the reaction in terms of later on. So first thing you always want to do is write yourself a balanced reaction. So we have our balanced reaction here. The mass. So they told us that it was 50 plus 50, so that's 100 ml, which is a volume. However, it gives us the density, and since it's 1 gram per milliliter, we could just say the mass is 100 grams. Specific heat is going to be 4.18. Change of temperature. So we had a final minus initial, so our final was 27.5 minus 21, which was our initial, which gives us a difference of 6.5 degrees Celsius. So we're going to substitute these values into Q equals MC delta T. So we have 100 times 4.18 times 6.5, which gives us 2717. Remember, since C is in joules, our answer is in joules, 2717 joules. Now remember, we just calculated the heat of the solution, but the heat of the reaction is the opposite of that. So it's negative. So the heat of the reaction is negative 2.717 kilojoules. So I just converted to kilojoules since we know in the end we're going to need kilojoules per mole. So from there, we have to convert our liters of HCl. So we have 50 mLs. I converted it to liters. So I could use molarity. 1 mole per 1 liter equals 0.050 moles because our delta H needs to be in kilojoules per mole. So our kilojoules is negative 2.717 divided by the mole amount, 0.050, gives us a final answer of negative 54.34 kilojoules per mole. So to kind of recap what happened there, we calculated Q for the solution. We turned the Q of the reaction the negative of that number and also converted to kilojoules in the meantime. Then we had to take whatever we're solving for, so in this case it was HCl, I had to get a molar value for HCl, and I do that by using the volume of HCl and then the molarity, which gave me moles. My final H has to be in kilojoules per mole, so I divided these two numbers to get my final answer. Next practice. So we have 0.243 grams of magnesium metal is combined with enough HCl to make 100 mLs of solution in a constant pressure calorimeter, and it gives us the reaction. If the temperature of the solution changes from 23 to 34, calculate the heat of reaction in kilojoules per mole for magnesium. Assume specific heat is 4.18. We're also going to assume that the volume of the HCl is going to be, again, 1 gram per milliliter. So first thing you're going to have to do is find the mass. The mass in this case, and this is very important, you're going to do this with all calorimetry problems unless it somehow tells you the total mass. You need to add up the two masses. So you have 100 plus 0.243. That's your mass. Your C value is 4.18. Your delta T is 11 degrees Celsius. We substitute that into Q equals MC delta T to get 4609 joules. That's the heat of our solution. I want the negative of that for our reaction. So the reaction, and I just converted to kilojoules already, negative 4.609 kilojoules. Now again, you have to go back because what do we want it in terms of? We want it in terms of magnesium. So you have to convert the grams of magnesium to moles of magnesium. Once you get that mole amount, you divide your kilojoules by those moles, you get around negative 461 kilojoules per mole. So you're really kind of going through this same procedure over and over. And as we're going to do 2 labs with this, so you're going to get very good at taking that lab data and making it make sense to find a heat of reaction. Another type of calorimetry that they don't ask as much of on the AP exam is bomb calorimetry, and this is at a constant volume. So your bomb calorimeter is used to study combustion reactions specifically, and the substance is placed in a small cup within an insulated sealed vessel. So that's like the bomb, you could call it. So in this picture, like here's a little bomb where the reaction is happening. So the heat released by this reaction is absorbed by the water and a change in temperature is produced. So it's the same like thought process that we've been using for the other one. It's just that in this case it's a constant volume. So in this case, we're just going to, as we know already, Q of solution equals negative Q of reaction. So instead of saying that, you could just say the Q of reaction equals negative C times delta T. So C cal is the molar. I'm sorry, not the molar. This is just the total heat capacity of the calorimeter. So these values kind of have already been calculated, a lot of them, and they have to calibrate the calorimeter. So if we know that 1 gram of benzoic acid produces exactly 26.28 kilojoules of heat, if the temperature increases by this much, you can find your heat capacity by dividing those two numbers and you get 5.431. Like I said, this isn't asked as much on the AP. You really just have to focus in on the calorimetry we were doing before. So here's an example. So if you're given this reaction, when 4 grams of CH6N2 is combusted in a bomb calorimeter, the temperature changes from 25 to 39.5. In a separate experiment, the heat capacity of the calorimeter was measured to be 7.794. Calculate the heat of combustion of a mole of CH6N2. So our Q of reaction is negative C of the calorimeter times delta T. Your heat capacity of the calorimeter is 7.794 kilojoules per degree Celsius. Your delta T was 14.5 degrees Celsius. So you're going to substitute that into the equation. Don't forget about that negative sign. Get negative 113.013 kilojoules because this was in kilojoules. So your answer is automatically going to be in kilojoules this time. Same process. You convert the grams to the moles, get 0.0868, divide these two numbers, kilojoules per mole, negative 1301 kilojoules per mole. So it's really essentially the same process, except in this case, you don't really have to worry about the mass because you're more concerned with the heat capacity of the calorimeter. So those are 2 types of calorimetry. Like I said, you need to be more familiar with the coffee cup apparatus because they like to usually ask a lab kind of related question where you're looking at different pieces of data. And like I said, we'll do labs about this so you'll understand how you can kind of analyze data to get a heat of reaction.